In this program, we'll cover the electrical diagrams in which many devices and components such as limit switches, push buttons, and so forth are used and represented. In fact, these devices are the ones which, when interconnected, form a control circuit. But what do we mean by a control circuit? What's a control circuit?
A control circuit is any circuit which has as its load device the operating coil of a magnetic motor starter, a magnetic contactor, a relay, a pilot light, or any other load, such as a solenoid. It is also, in general, a circuit which exercises control over one or more other circuits. The elements of a control circuit include all the equipment and devices which are involved with the function of the circuit itself. These elements also include conductors, raceways, source of energy supplying the circuit, overcurrent protecting devices, all the relay coils, contactors, and starters, as well as all switching devices which govern the operation of the machine or process being controlled. These control circuits are represented in electrical drawings or diagrams which essentially give you the complete storytelling of the process or machine control, from the sequence of operation and instructions to the location of the components which form the control circuit. These diagrams are called ladder or line diagrams, layout and connection diagrams, and wiring diagrams. Ladder diagrams got their name because they show the sequence of operations in separate lines which resemble the look of the rungs of a ladder as we know them. One step from the top leads to the next step down, and so on. The ladder diagram provides two important pieces of information, the first one being the power sources, and the second one, how the current flows through the various parts of the circuits, such as contacts, limit switches, push buttons, and so forth. A ladder diagram is intended to give you the basic operation of the control system. A layout and connection diagram gives the physical placement or location of all the components in a control panel, while a wiring diagram, like this one for a magnetic starter, is intended to show you the actual physical relationship of all the various devices that form the control system. Note that the heavy lines are used to represent power circuits, while the thin lines are used for control circuits. Now let's go into more detail about ladder diagrams and some basic rules that must be followed in the implementation and interpretation of electrical control ladder diagrams. In fact, when you are reading or interpreting ladder diagrams, it's important that you understand these basic rules. There may be many ways to connect or wire a circuit, but in the electrical industry, there is an established set of symbols universally known and rules on how these ladder circuits must be laid out. First, let's look at a very simple ladder circuit in pictorial form, in which we have a normally open push button connected to a pilot light. One side of the push button is connected to the power side, which is L1, while the other part of the push button is connected to the load. In this case, the light. The pilot light, in order to complete the circuit, must be connected to the L2 line. In this simple pictorial ladder circuit, we can see that if the push button is pressed, it will provide power to the light via the connecting wire and therefore turn the light on. If the push button is released, then the light will lose its power and will turn off. When there is power going from L1 to L2, connecting or giving power to each device, we say that there is power continuity in the circuit. In fact, continuity is said to exist if there is a power path from left to right. We know that it would be very difficult to represent all the control devices in a pictorial manner, and that is why we use their appropriate symbols in an electrical ladder diagram. By simply replacing each of the components, in this case the push button and the pilot light, by their respective symbols, we would obtain a cleaner, more descriptive circuit. This control circuit is understood in the same manner. If the push button is pushed, it will provide power continuity to the light, which will glow. If the push button is released, the light will be off. In a ladder diagram, we place a large, bold node where there are actual wiring connections when two wires cross each other. This is also better shown in this other ladder circuit where the contacts CR1-1 are connected across the start push button. Let's now go over some of the basic rules that have been established throughout the years on electrical ladder diagrams. It is important for electricians and technicians to master the reading, interpreting, and keeping of the basic rules we're about to cover so that everyone at your plant can follow a standard format. Among these basic rules, we have the use of one load per ladder diagram line, the requirement that loads be connected to the L2 line, that control and switching devices be connected between the hot, or L1, and the operating coils or loads, and that each line be numbered for easy reference in the ladder diagram. The one load per line rule simply states that only one load may be connected between L1 and L2 for each line. For instance, if we have a simple switch controlling a light and also a heater, we would not connect the switch to the light and to the heater like this. Here, two loads, the light and the heater, are both in the same ladder line in between L1 and L2. The desired function here is that both loads are turned on when the switch is closed. So, to properly apply one load per line rule, we would have to redraw the circuit like this, where there is only one load per line between L1 and L2. When the switch is closed, both loads will be energized or turned on. In this wrong configuration, when the switch closes, neither of the two loads will receive the entire 120 volts, which are required for proper operation, and therefore will result in a fault. In the correct configuration, both loads get a full voltage between L1 and L2, which is required to properly operate. If we place a voltmeter across each of the loads, we would read 120 volts AC. As it can be seen so far, all the loads, such as control relays, pilot lights, and solenoids, are connected to L2, completing the circuit from L1 through the control and switching devices, such as limit switches, push buttons, and relay contacts. The reason why loads are connected to L2 and not like this is because we always want to switch the power or hot lead to the loads for safety reasons, as opposed to switching the return line like it's described in this diagram. Here, the solenoid is always powered, waiting for a switch connection to the return L2 line. One small exception to the rule that the loads be connected in the ladder diagram directly to L2 is in the case of motor starters. The graphic ladder diagram representation for the coils of motor starters is slightly different than a regular control relay simply because of the overload contacts. We know that magnetic motor starters contain the normally closed overloads, which are indirectly connected to the coil through some wires placed when the starter was manufactured. To get a better idea, let's look at a simple, single-phase manual starter with overloads. In this pictorial one-phase motor starter, we can see that the pilot devices are connected to the motor and to L2 through the overloads to complete the circuit. It would be logical to represent the ladder diagram equivalents of this circuit like this, where the overloads follow the switch. However, in control circuits with overloads, the ladder representation is like this, where the overloads are shown after the motor load. As we'll see later on, the decision that governs the response of a load is represented on the left side of the load in the ladder diagram. The overloads do not really decide on whether to turn on or off the motor load, but rather they monitor in a protective manner the operation of the motor. That's why, if we represent the overloads on the right side of the motor is really the one which controls the status of the overloads. If the motor starts to pull too much current, an overload will trip and its contacts will open. The number of overload contacts between the starter coil and L2 depend on the type of starter and the power used in the circuit. For instance, a three-phase starter may have three normally closed overload sets of contacts, which will be shown like this in a ladder diagram. To avoid confusion and simplify the labeling in a ladder diagram, we represent these overloads like this, where the mark all OLs or all overloads are represented from the starter coil to the L2 connection. All the control switching or pilot devices that determine the operation of an operating coil, control relay, or a load are connected and shown in a ladder diagram from L1. These devices are wired in several logic configurations, as we'll see later on, so that the proper activation of the load or control devices is achieved. For instance, either of the two push buttons here will turn the light on when pushed. Regardless of how all the devices are arranged in a circuit, they must be connected between L1 and the loads. Each line in the ladder diagram is identified or referenced by a line number. These lines are marked 1, 2, 3, and so on, depending on the size of the control system. These lines start at the top and read down in the circuit. A line can be a complete path from L1 to L2, each line, of course, containing a load. Note that lines 3 and 4 have the same load, and two different line numbers are assigned because there are two complete paths to the timer, from L1 to L2. An independent line number will also be assigned to a set of contacts like this, coming perhaps from a master control relay. Line numbering is important for understanding the function of a circuit because it will reference also the use of control relay contacts in a circuit used for interlocking. We'll see more on this a little later. It has been proven that following and sticking with standard ladder diagram rules are of tremendous benefit when interpreting a control circuit. This is especially true when the circuit you are reviewing or troubleshooting has all its references up to date. There are situations, however, in which changes to a machine must be performed, and you may be assigned to the task of making changes to a control circuit of a particular machine, or even design from scratch such a control circuit. In this case, not only following the rules of ladder diagrams will be helpful, but also a knowledge on how to generate and create the outputs necessary for proper operation. With this in mind, let's look at the composition and creation of control output based on desired inputs or situations. A control circuit is composed of three basic sections: an input section, a logic or decision section, and an output section. From L1 to L2, these sections can be represented like this, where one or more control and switching devices will control the action of a load. The input signals that are used in the definition of a ladder circuit can be generated in a manual or automatic manner. By manual, we mean that the input signal is activated by a person such as an operator. These include push buttons, foot switches, selector switches, and others. An automatic signal generation is one which corresponds to the input information provided by sensing switches, which give position, volume, and flow, or other kinds of relevant information about the process or machine. For instance, a float switch, which is activated automatically when water reaches a desired level, can be considered an automatic control. Regardless of whether these signals are manual or automatic, they do not operate as an output load, thus they perform no work. They simply provide information, input information, to be used to make a decision on the behavior of an output control. The logic section of a circuit is considered as the decision maker, where, depending upon how we want an output to take place, the wiring or interconnections of the input signals will be performed. We'll cover in detail this area in a little while. The output action is the result of a circuit responding to the input conditions to render, according to a logic, an output device which performs an action, whether directly or indirectly. Direct action outputs include control relays, solenoids, pilot lights, and others which are actually operated directly from the input signals according to a logic sequence. These outputs perform the work in a direct manner. Indirect action includes devices such as magnetic motor starters and high current heating elements. This output action is indirect because, like in the case of a motor starter, even though the starter coil is energized, it is not the one which actually starts the motor that causes output work. The coil, when energized, makes the contacts of the starter close so that the motor starts. In the case of a heating element, The heater control relay is the one which activates the heater to provide work, in this case, to raise the temperature. Regardless of whether the output control is direct or indirect, the loads are activated by the control circuit through the reading of input signals and the definition of its logic decisions. Let's now take a look in more detail at the logic or decision section of the control circuit. Logic, as used in control circuits, can be defined as the necessary arrangement of input signal conditions that need to take place to cause a control output. This arrangement is implemented by the interconnecting wires of the circuit. It is obviously apparent that the organization and documentation of the control circuit will define how complicated it will be for someone else to figure out what you have done. There are three basic types of logic functions, which are the AND, OR, and NOT. These functions nearly cover all of the possibilities you may encounter in a control circuit. The AND logic function simply states that for an output to occur, all of its input signals must provide power continuity from L1. Or, in other words, all the input signal devices must be conducting current. For instance, assume that we want the pilot light, the output, to turn on by the input signals provided by the push button PB1 and PB2. An AND function will be used if we want the light to be on if PB1 and PB2 are pushed at the same time, thus providing power continuity to the load. This AND logic simply dictates that if both push buttons are providing power, the light will turn on. If we added another AND input signal condition to this circuit, such as a pressure switch, it would mean that the pilot light will be on if both push buttons provide power and also if the pressure switch is closed. This AND logic says that all three elements are wired in series for the output to occur. As can be seen, the devices form the logic by the way they are wired or connected. The OR logic function describes the result of an output if at least one of its input signal conditions provide a path from L1 to the load to L2. For instance, this OR logic simply states that if PB1 or PB2 is pushed, then the light will turn on. The wiring configuration described by the OR function in this ladder diagram circuit is said to be a parallel connection of the two push buttons, or that PB1 and PB2 are in parallel. Note that the connection from PB2 in line 2 to PB1 in line 1 is shown by a node to indicate a junction of wires or conductors. The OR function in fact implies that if one or more of the input signals provides power from L1 when activated, then the output will be energized. Most control circuits will be a combination of AND logic with OR logic to control an output. Logic like this, which in this case drives a pump's motor starter, is created according to the need that you have, or better yet, according to the necessary conditions that must be present to activate the pump motor. The logic of this circuit can be read simply by saying that the pump will be on if the temperature reaches the right level, thus activating the temperature switch TS1 to provide power, and if the flow switch is activated. Then the logic will be ready to turn on the pump if the push button PB1 is pressed or if the foot switch is activated. Notice that the logic simply follows what we want to happen, or in other words, the conditions that we want in order to turn on an output. So, if you are modernizing or revising a control circuit for the activation of an output device, just write down using the AND and OR logic to set up the conditions. The last logic function is the NOT function. In the previous AND and OR functions, we used devices as input signals which were in the normally open state. That is, the devices were normally open contacts or limit switches. However, we could have also used normally closed devices. The NOT logic simply uses the normally closed state of the input device. For instance, The pilot light will be on if the push button PB1 is not pushed or activated. Since this push button is normally closed, power will be passed from L1 so that the light is turned on. Another way to look at a normally closed device is that it is not normally open. In a ladder control circuit, an output will be on if the signal is not present or the event is not happening. If it happens, then the switch will open and the output will turn off. The input signal must remain closed, providing power from L1. The NOT function is used a lot in control circuits because a lot of devices we want in the normally closed position. For instance, all stop push buttons are normally closed, so that if someone pushes it, it will break or stop power continuity to the circuit. Remember that you have available normally open and normally closed contacts from switches, push buttons, limit switches, and other devices. And depending upon what you want to do and how you are going to do it, you'd have to determine which contacts you will use. Let's take an example we see every day when we go to work. When we open the door of the car, the light inside turns on, and it will turn off when we close the door. We know that in the door there is a small switch which is pushed when the door is closed and released when the door is opened. If from this switch we have available a double pole, single throw, double break set of contacts, one normally open and one normally closed, which one would we choose to implement the logic and come up with a ladder control circuit which simulates the car door light circuit? Let's see. The function of this switch goes like this. If the switch is pushed, the normally open contacts will close, while the normally closed contacts will open. This will happen if the door is closed because it would push the switch. Now, to clarify our thoughts, we need to think that we want the light on when the switch is not pushed because the door is open, so we would connect the normally closed to the light. Every time the door is open, the switch will be released and the light will be on. If the door closes, then the switch will be pushed and the normally closed contacts will open, thus disrupting or breaking power to the light. We could very easily make this circuit operate in all the doors of our family car. The logic or decisions to be made simply states that if any of the doors open, meaning an OR condition for the doors, then the light will be turned on. As we can see, we created a control circuit according to the needs for the desired operation of the output. This circuit could very well be used in a control panel which contains the electrical components that form the control circuit. We could further enhance the circuit by saying that if the panel door is open, we want, in addition to the light being on, to cut off the power to any other part of the circuit. This can be done simply by adding a control relay. Let's call it CR1 in line 2 and using its normally closed contacts to provide the L1 power to the rest of the circuit. If the door is closed, the switch will be pushed, opening the switch contacts. Thus, CR1 will de-energize and its contacts CR1-1 will remain closed, providing L1 power. If the door opens, there is power to CR1 and the normally closed contacts will now open, disrupting power. But what if your boss asks you what happens if someone needs to troubleshoot the circuit with the door open and needs the power? The easiest way to solve this problem is to state it like this. If the door opens, we need to bypass the power that has been cut off by the contacts of the control relay CR1. This can be done by placing another set of contacts in parallel to CR1-1. By creating a signal that says we want to troubleshoot the system, even though the door is open, we can control these contacts. If we add another control relay CR2 and we label the parallel contacts CR2-1, we can create the bypass and control it with a signal from a selector switch inside the panel which creates the signal troubleshoot. If the selector switch is in the troubleshoot position, the relay CR2 will energize and the contacts CR2-1 will close, thus passing L1 power to the rest of the circuit. If the troubleshoot switch is not selected, CR2 will be de-energized and the CR2-1 contacts will open. The selector switch for troubleshooting may be a key operator selector switch to provide for authorized use only.
In Part 2, we'll start by going over how we add memory to a circuit and the different methods used to interlock these control circuits. Then we'll cover the complete representation and interpretation of more complex ladder diagrams. We'll then go over in detail on the subject of wiring diagrams.